like to just take a minute here to introduce Martin. I think many of you may know him already, but it's our pleasure to have Martin here giving a MechSE departmental seminar. Martin started as a faculty member at MIT in mathematics back in the late 90s, I believe. And
that's right, yeah. Time flies.
Chemical engineering, and those appointments of Martin's really reflect the blend of physics-based understanding that he brings with mathematical modeling. And I have to say he's really been a role model to me in a number of ways in that regard, and I think to a lot of others. And he's made seminal contributions in the fields of electrokinetics and electrochemistry, and has been a fellow of APS, ISE, the Royal Society of Chemistry, and received numerous awards. And we're very excited today, Martin, to have you speaking on this very timely topic of COVID-19 transmission. And we just thank you again for being here. Let's give our speaker a warm welcome.
Great. Well, thank you for such a kind introduction, Kyle. This is an experiment. Actually, this is my first talk that is not on topics like the ones you just mentioned. So I've been working very hard on this topic. In fact, almost like living and breathing it for the last, almost a year now, I guess. But this is my first formal seminar on this topic. So I'm really glad to have the chance to share that with you, and look forward to your questions. And I'm sorry I couldn't be there in person, but hopefully, that won't be so far off for all of us. Okay. So let me get started then. So is the corner of my screen blocked right now, or is that okay? I was wondering if
it's not blocked. It's good.
Oh, okay, great. So we're just seeing the. Okay, great. I wasn't sure. Okay, so this is work that was is primarily with my colleague John Bush in the math department. Although I'm also going to present a number of other items as well. And the title is Beyond 6 Feet: A Guideline to Limit Indoor Airborne Transmission of COVID-19. So this topic doesn't need too much introduction, but maybe just briefly to give an overview of the situation we're all in right now. So the COVID-19, or coronavirus disease 2019, began just over a year ago as an outbreak in Wuhan, China. Interestingly, even as late as February, it was still called the Wuhan coronavirus by Time magazine, as you can see here. And here's documenting on the left the initial spreading from Wuhan across China, and on the right, a little bit later, the spreading across the world. So it was obviously quite infectious. I actually was going back to look to see what's the situation. I've been following actually China. They've admitted now to 63 cases right now, which I have been puzzled by those numbers for a while. And I just read actually a couple of days ago, they've locked down another city. So I have to imagine there must be a few more than 63 cases, but nevertheless, they initially had a very large number of cases, and that led to then everything else we see in the world today, which is sort of documented here. So there was sort of an initial wave in the spring in many places. And of course, there's been sort of second waves, which are peaking in many places right now, especially you can see the United Kingdom is now overtaking the United States. There have been many cases, and we're up to about 1% of the global population. There have been a lot of deaths, although to put it in perspective, we're still at 1% of the normal deaths that would occur. But that's obviously still getting to be a large number, although not near the levels of influenza of 1919. And of course, it spread around the world. So now some aspects that are worth noting are that the death rate or the mortality is not what it appeared to be at the beginning. So if you look, for example, at Massachusetts, and this is similar in many places, we had an initial wave, if you look on the left, where there was a certain death rate, which was reasonably high, I guess 200 in one day versus 2,000 cases at that time. Now in our second wave here, we have maybe 4 times as many cases, but only half or fewer as many deaths. So at least something is changing in terms of either how we're responding or the virus itself. And of course, there are mutations going on as well, as many of you know. One aspect could be the middle plot here, which is there's a very strong sensitivity to dependence of age in terms of the outcomes from COVID-19. So this was already apparent, beginning to be apparent actually early in the spring, but certainly by summer, it was pretty obvious that for young adults, in fact, people under 25 at that time, there were only 200 deaths, and that kind of rate has maintained, whereas those very large numbers I talked about are very much focused on the elderly. And in addition to that, there's a pretty strong sensitivity to pre-existing conditions. So even moderately elderly people who don't have other comorbidities do tend to fare relatively well. So I think by recognizing the populations at risk, that has helped us to combat this. On the other hand, another interesting aspect is that a large number of cases are asymptomatic. There have been many different estimates, but it's a significant number, and especially in the younger age groups, it's believed to be a much larger number. As you can see, the hospitalization death rates are very low, even symptom rates are relatively low, but the transmissions could be higher, and there's debate on it, but children, for example, are believed to be transmitting at a rate anywhere from 2 to 4 times less than adults, but not as much of a difference as you see here in terms of the outcomes. So that's just a bit of background. What I want to talk about today is how does COVID-19 spread? And once we understand that, then we can talk about how to fight it, which is actually how I got interested in this topic in the first place. So here's a nice slide, which I borrowed from a nice review article of Donald Milton, which talks about different potential modes of transmission for respiratory pathogens, such as the virus SARS-CoV-2 that causes COVID-19 disease. So basically, there are 3 basic ways. So through breathing and exhaling droplets that may contain the virus. Those droplets can then be transmitted in several ways. One is by fomites, so that those droplets could end up on surfaces or on your hands, and then you touch somebody else or someone else touches the surface, and then they touch maybe their eyes or their nose, and eventually the virus gets back into the respiratory tract. There's not very good evidence of fomite transmission. In fact, there's very weak direct evidence and growing circumstantial evidence that fomite transmission is not a major mode for COVID-19. There's also the mode of large ballistic drops. So in particular, when you cough or sneeze, of course, rather large droplets that you can see that might be at the scale of millimeters even, or hundreds of microns are ejected, and they can go a fairly long distance, but they're heavy and they settle out. And those are sort of the ballistic drops. And perhaps you've seen some of the beautiful images. In fact, my colleague John Bush actually studied violent expiratory events such as coughing and sneezing and tracked where the particles go. But there's a third mode, which is related, which is the so-called airborne or aerosol route. And that refers to particles which are so small you don't see them, and also which remain suspended for long periods of time. So these are particles that are around the micron scale. And as you may know, those are actually very common in your respiration. So here I just give in the middle, actually, a typical, this experimentally measured distribution of droplet sizes from different, it does depend on the activity, but it roughly always has this basic shape here, where the peak, so the most common droplet size is actually around 1 micron. So that is an aerosol droplet that will stay suspended in the air for a very long time. There are these larger droplets, and when you're just, say, talking even, you actually may not realize it, but when you open your mouth, you're breaking fluid films and essentially spitting out tons of droplets, which are at that scale of hundreds of microns, as we can see here. That's a millimeter scale bar. This is from recent work of Abkarian and Howard Stone at Princeton. And when you cough and sneeze, that you get even more of the larger droplets. But what I really want to focus on are these small droplets. And it's not known exactly how they are created. And there's some interesting research still that needs to be done, and that I'm actually myself interested in on that aspect. So one mode of generating the aerosol droplets is bronchial film bursts. So basically in the bronchioles, which are the smallest kind of passages in your lungs, which end in the alveolus, where the exchange of oxygen is happening, those are flexible tubes that are essentially collapsing and then reopening as air is coming in and out when you breathe. So when you breathe in, you open up those passages. It causes the films to stretch and then rupture and form some droplets, which then get blown out when you exhale. A very interesting thing that's become apparent this year, and in particular with the research of Moravska, which in fact goes a bit further back to 2009, but also Bill Ristenpart, a chemical engineer at UC Davis, starting a year ago, in 2019, is that there's a very strong correlation with speech and also the volume of speech and even greater vocalization such as singing. So as shown in this picture here, this is actually a zoom in of the glottis or the vocal folds in your larynx or your voice box when someone is just simply speaking. And these flaps are vibrating at about 100 hertz. And as you can see, there's plenty of liquid and mucus linings there, which are getting stretched and broken. And so it makes sense that there would be a very significant droplet generation going on here, depending on your vocalization in addition to just simply breathing. So we'll come back to that aspect in just a moment because it turns out to be very important. So now that we see that there are drops generated by breathing, then we have to ask, what is the fate of those drops? So this entire field was essentially founded by Wells in the 1930s, very seminal, beautiful work, both analytical and experimental, in studying coughs and sneezes and thinking about respiratory disease transfer. So he pioneered this concept of the Wells curve, which is simply comparing the settling time for a droplet, which if you just use Stokes' law scales like 1/r squared, where r is the radius of the drop, and comparing that to the evaporation time, which in a simple vapor diffusion limited analysis scales as r to the power positive 2, so r squared. And so the Wells curve is shown here as a function of the droplet diameter across the horizontal axis. Then the time to either settle or evaporate is shown going down. So these vertical lines represent sort of like a drop falling, and which of these curves you hit essentially tells you the fate of that droplet in this analysis. So what you find is that droplets that are small tend to evaporate first, and those that are large don't evaporate, they actually hit the ground first. And in fact, also as a result of his experiments, he found that those droplets from coughs and sneezes often settled out at about 2 meters. And as I understand it, this is the origin of the 6-foot rule, the scientific origin. Now you can imagine at that time, he had no fancy cameras to really detect any smaller droplets and couldn't do simulations or a lot of the aerosol analysis I'll be showing you. But that was a very pioneering work at the time. Now, one thing that Wells recognized, which I think though was not fully recognized even today in the field, is that the picture up here is missing one very important aspect, which is solutes. So the evaporation time here is to essentially evaporate completely and depends on the relative humidity and the size of the drop. But in fact, saliva has about maybe a few percent of solutes, such as salts and various proteins, but especially those generation of droplets in the deeper part of the respiratory tract, as I showed you. The liquid there is a non-Newtonian fluid, basically mucus, which contains mucin proteins and other macromolecules that are charged. And in fact, there can be a very significant fraction of solutes, even 10% or so. So if you just redo the evaporation analysis, and there's a very nice detailed analysis by Netz recently on that problem, you can see that actually that kind of cuts off the shrinking and leads you to an equilibrium size. And Wells already anticipated that. He spoke of droplet nuclei. He imagined that the water would evaporate, but leave behind some of the pathogen, these other molecules, and also some bound water. And that's exactly what does happen. And so we actually are generating droplets that are stable, that are in the size range that I showed you was experimentally measured. And so we have to think about those. So certainly the possibility of airborne transmission is there, where these aerosol droplets are breathed out by one sick individual and then breathed in by someone else, making them infected. I can't go through all the evidence here, and I've already made a very busy slide here, but it's my opinion and the opinion of many other scientists that airborne transmission is not only possible, but is actually the dominant mode of transfer of COVID-19. Just to give a few of the important examples, which I will come back to, first of all, we can look at super spreading events where one index case infected a large number of other people. There's a catalog of those. In fact, you can go to this website, I list here, and see that database, which is growing. And there's over 1,000 of those events, and every one of them has occurred indoors. So certainly sharing indoor air appears to be relevant, but also these specific cases, which I will be analyzing later, listed in blue here and shown in the pictures, give further evidence. So in the bottom right, you see a performance of the Skagit Valley Chorale, a singing group in Washington State. And it turns out one of the first outbreaks in the United States was at one of their choir practices. And one infected individual infected 86% of the others. So that was 53 out of 61 in a 2.5 hour choir practice. And 2 of them, as a result, died, actually. So it was a very bad outbreak. But looking more closely at it, there really was no close contact. There's a large number of people, a short number of time. You can't say that they all shook hands or breathed in each other's faces. So that's one good example. There's also a bus ride to a Buddhist temple in China that was documented, where one person on the bus infected about a third of the others on a relatively short ride. And there it was determined there was no correlation with the seating on the bus. So if you were sitting just in the next row or all the way in the back, the probability of infection was about the same. And then there's also the Diamond Princess cruise ship, which is shown here. So that was where there were some cases detected, and the ship was quarantined in Japan, in Yokohama. And in 12 days, there was, starting from a small number of cases, which I estimate was perhaps around 20, fewer were detected by then. At the end, there were 354 cases out of almost 4,000 people on the ship. And it was determined later that the sort of new and subsequent new infections were not correlated with any clear contacts. In fact, including people that were, it didn't raise the risk that much to even be in the same room compared to being in neighboring rooms in some cases. So that's just sort of somewhat circumstantial or epidemiological evidence for spreading. There's also statistical evidence. One recent study analyzed all the initial outbreaks outside of Wuhan and Hubei province in China. So looking at all the first cases in other cities in China outside of that province. So that was over 7,300 cases in 320 cities. And they analyzed the initial transmissions that were known. And so those are called then outbreaks. And there were 318 outbreaks. And of those, which include, in this case, 2 or more transmissions, they were 80% in family apartments, and 34% also may have involved public transportation. And of all those events, only one documented transmission, which was to one other person, occurred outdoors. So clearly being indoors and sharing time together without masks, by the way, because even in China, this was all before any masks were being worn in those places, that seems to be a problem. Finally, infectious virus or virions that can replicate their DNA have been established in the droplets that are emitted by breathing. For example, in a recent study of Lednitsky, in a collection point 16 feet away from sick patients in a hospital room, and also in a nice study of Santarpia, where they actually broke down the droplets by size from actual infected patients and found not only that the virus was present in the aerosol droplets below 4 micron diameter or radius, or diameter, I should say. They also found that those were the most infectious. Now, as chemical engineers, this makes a lot of sense. If you want to transfer a molecule to another site, well, what you want to do is put it in a system of high surface to volume ratio. So very small particles, it's very easy for the virus to diffuse in and out. It's very easy to get to the deepest parts of your lung, etc. So it even makes sense, actually, that there would be even physically higher infectivity in that range. So while the evidence, I think now, a year later, is really quite strong and overwhelming, even early on, many scientists were kind of raising the alarm about aerosol or airborne transmission because it was not recognized by the public health agencies. So I mentioned Bill Ristenpart. So he wrote a nice article in the beginning of April, basically pointing out that COVID-19 could transmit through aerosols. Lydia Marosco has been working on this topic for a very long time and was the author of the study I showed in 2009, looking at different types of respiratory droplet transmission, and has studied many diseases as an epidemiologist over the years. Wrote a very blunt paper here, Airborne Transmission, the World Should Face Reality. And this was back in the 10th of April. It was published and written even before that. Unfortunately, it did not gain the attention perhaps it should have. Then she and Donald Milton, with 239 other scientists, and I myself would have added my name if I had the chance, essentially wrote an open letter to the World Health Organization saying that the coronavirus is airborne. Now, that did prompt the World Health Organization to acknowledge airborne transmission in July, but still they have not acknowledged it to or endorsed it to be a dominant mode of transmission, and nor have they provided quantitative ways to fight it. Now, the CDC was a little bit, or in the United States was even a bit behind that. They actually posted guidance on airborne transmission in September and then took it down and then brought it back. And so they finally have confirmed that airborne transmission is possible, but still at that time believed not to be dominant in October. So this led to a lot of discussion, obviously, and even in the Lancet Respiratory Medicine Journal, there's a really nice quote essentially setting up the work that I'm trying to do, and others as well. Public health guidance now needs to advise people how to navigate risk in indoor settings, and specifically looking at airborne transmission. So that is the basic motivation here. Now, how did I get into this? It started with the observation that, at least in my world at MIT, and then also in my children's schools and in various businesses that I know, these places were all being shut down or having limited occupancy based on one thing, which was the 6-foot rule, which, as you can see, these people here, for example, measuring desks, like somehow that distance, you're gonna be very safe. But if you were sitting at this desk that's maybe only 4 feet away, that would be unsafe. And so the problem is we don't have the floor area in the United States or anywhere, frankly, to keep people exactly 6 feet apart at all times. None of these spaces were designed that way. So, and by the way, that rule, though, is specific to the United States. In Netherlands, they recommend 1.5 meters, and in the World Health actually has all along recommended 1 meter, which is closer to 3 feet. So, but in any case, there's a recommendation of distancing. More recently, and I think influenced by some of the work on airborne transmission, you might have noticed that various governors in the spring, like at Thanksgiving, were recommending limits on gathering size. So Oregon said 6 persons, Minnesota and Massachusetts was 10, Massachusetts was 25 at that time, California was 3 households. So clearly there's a recognition that maybe the number of people matters. Also, there was limits on outdoor gathering size. Oddly enough, for a while, MIT's outdoor gathering limit was smaller than their indoor gathering limit. It was 10. So I never could understand that, but we've moved past that now. And then there was also a growing recognition that maybe ventilation rate needs to be controlled. So for example, the regulatory group in the United States, ASHRAE, had recommended at least 6 air changes per hour, which is a good advice. And in the UK is a similar restriction. In Germany, as they've actually been recognizing airborne transition more, they've recommended you should open the windows for 5 minutes after 20 minutes in a space with the windows closed. And then finally, time is also somewhat noted in the sense that the CDC defines a close contact for contact tracing as being within 6 feet of an infected individual for more than 15 minutes. And so I'd like to highlight here in the blue is really just what is common sense when you start thinking about it. If you think of how the transmission is happening through droplets that are being exhaled and inhaled by somebody else, and knowing something about fluid mechanics, you should be a bit concerned about any one of these prescriptions. But perhaps even more common sense is just recognizing that bounding one of these variables can never be enough. Take, for example, the gathering size or the distance. If I have people 6 feet apart with at 50% capacity in a room, and we enter that room for only a few seconds, we're obviously safe. There's no chance of transmission. But if we stay in that room with poor ventilation over a period of days, it's pretty likely there's going to be a transmission. So those variables are obviously coupled. And the only example I know so far where a guideline has showed this coupling was for Thanksgiving. California said no more than 3 households, and then they added later for no more than 2 hours. So now you can ask the question, if we're going to make specific guidance like that, what is it based on? Where's the science? And also, what if we wear masks or test regularly? Clearly, that should affect whatever guidance is given on these variables. So that's a bit of the motivation. By the way, this on the right here is myself. I'm waiting for the in line for my COVID test at MIT, and it's snowing and we're outside, but see the blue tape on the ground, we're still 6 feet apart. Okay, so this now brings me to my work. I'm going to leave out some of the technical details and really just try and emphasize the main ideas here. So here's just kind of a summary of the equations. It's nothing fancy. This is really undergraduate level chemical engineering or applied math, or in fact, models that you would find in many other fields as well. Essentially, the simplest way and most general way to model airborne transmission is to do essentially a mass balance for the concentration of virus in these droplets in the room. And in the language of chemical engineering, the model is essentially a continuous stirred tank reactor. So you assume the room is well mixed. And this type of model actually has a long history. The very same Wells that I told you about by the 1950s had developed a model which was later popularized by Riley for measles in the 1970s, which is now this class of models called the Wells-Riley models. And it's essentially a continuous stirred tank reactor. So the way the model looks, I just give the basic equations here, is that there's a concentration of let's say pathogen in the air per air volume, and you write a mass balance where P here is the production rate, and then there's a removal rate for various processes. And the only slightly different thing that I've done in my work here is to really take into account those actual distributions of droplet sizes, take into account that they're produced differently at different sizes and also removed at different sizes. So we're just simply resolving things here by radius. The production rate is the product of the breathing rate, QB, which is about half a meter squared per hour for typical respiration. CV is sort of a microscopic virion concentration in liquid. ND is the droplet size distribution, which I showed you some examples of and is sort of sketched in the upper left. VD is the volume of the drops, and PM's then also the mass transmission probability. So to produce it, if you are masking or filtering, it has to, of course, get out as well. And that is dependent on radius as well. And then if we look at the removal rates, there's 4 different processes. One is ventilation. So there's even though some air may be recirculated, there is a net flow of outdoor air through that room. And that's what I'm calling here lambda A. So that's the flow rate of outdoor air per volume of the room. So that's also called the outdoor air change rate. There is a sedimentation rate. So using Stokes' law, essentially you can write that as something which depends on R squared relative to a critical size, which depends on Stokes' law and also this ventilation exchange rate. So to sort of where is the critical cutoff for particles that you're going to find in high quantities in the room depends on the ventilation rate, on how quickly you're moving them and on how fast they're settling. So there's kind of a typical droplet size that's actually in the room, which does require solving that mass balance. Then the third term is filtration. So if a certain amount of air is recirculated and filtered either through a freestanding filter or through the ducts, then you can also define a filtration air exchange rate, and that will be multiplied by a filtration coefficient, which it tells in this case would be a passage. The way I've written it, PF is the probability that a particle of size R passes through the filter. And finally, the virus also naturally deactivates in the droplets and also potentially on surfaces. There are some measurements of that and also some theory. That's something I'm actually working on right now. There's some interesting chemical engineering there in that the dependence on relative humidity, for example, is quite interesting. As you probably know, the seasonal flu and perhaps also it is believed also the coronaviruses that cause COVID-19 are more active in the winter when it's dry. And that is because essentially the evaporation happens so quickly that the virus is not exposed to various solutes and salts that otherwise would be in higher concentrations in a partially evaporated droplet, and which can slowly deactivate the virus. So there's still study on that, but there's some known mechanisms. Also, UV light and other disinfectants can be lumped in here as well. And once you have this, you can solve this model and find what is the transmission rate between any 2 people in that room. And since it's well mixed, it doesn't matter in this approximation where they're positioned. So another factor of breathing rate comes in because now the susceptible person is breathing and they're breathing in the concentration. And then they also have another mass factor because they're filtering on the way in. So the bottom line is that the transmission rate scales like the breathing squared, but importantly, the mass factor squared because it's at each person's site, and something which I call CQ, which is the infectiousness of the exhaled air. If you multiply that by the breathing rate, that's also known as the quanta emission rate, where quanta is a concept introduced by Wells also, which is essentially measuring the rate of transmission. So you can express a transmission rate, this beta, as an exchange of infection quanta per time. And so when you take that perspective, you can also define how many infection quanta there are per volume in a breath. And that's what I'm calling here CQ. Now, I also want to note that there are other scientists who have worked on these types of models, including before me. And I mentioned Lydia Moravska, Jose Luis Jimenez at Colorado also is another leader in this field, and there are others as well. What I want to emphasize here from my work is, first of all, take into account what I think are the most important variables, including the size dependence of droplets and respiratory activity, but also to somehow simplify things enough that I can actually get a formula and to get a guideline that really shows how the different variables are related. Because typically in this field, and you can find other spreadsheets online or calculators, there's a solution to some equations, you put in a bunch of numbers and you get a bunch of probabilities or numbers out. And I really wanted to show more clearly sort of what's the relationships between the variables in a way that gives us a simple formula. Now, before coming to that, we have to parameterize the model. And so the way I've done that is by looking at the best characterized spreading events where the physical properties of the room that I need are actually known. Unfortunately, there are very few cases of that. So one of my main messages here is to the public health community is really when you document a spreading event, write down the physical characteristics of the space. So estimate the room volume, find out something about the ventilation and filtration that might be going on in that room, get the time that people spent together, record even the people that didn't get infected. So sometimes they record one person was infected and then 5 more were infected, but they didn't tell you how many people didn't get infected. So to do this analysis, you need all that information. And unfortunately, in very few cases we have it. However, that choir, the Skagit Valley Chorale, is one of those cases that's been very nicely analyzed, actually in a paper of Miller and Rofska from earlier this year. And so we have that information. And so what I have done here is to take the solution to, in that case, the Wells-Riley model, where we have one infected person and we assume slow incubation, where there's no newly infected people, they just get exposed. And that gives this kind of exponential approach to everyone getting infected. And if you apply that model to the data, you can back out the disease parameter CQ. But to do that, you have to take into account the activities in the room. That was a choir practice, so it's very important to recognize that that was singing and not so much, these other activities. And it is known even from the work of Moroska 2009 that singing is about the worst thing you can do. And it does correlate with that being a bad situation. And from the picture I showed you of the voice box, you could imagine when you're singing, you're pushing really hard, vibrating a lot, and clearly you're maximizing your droplet emission. And here's actually an example of that. So here's what I've done. I've scanned in the data for droplet size distribution from Rofska's 2009 paper, but then evolve them in the room. So basically taking the Skagit Valley Chorale volume and estimates of ventilation and all that, and floor area, we can then say, okay, in that room during that time period, what was the average background concentration aerosols now resolved by size? And you can see if I take the distributions for different types of respiratory activities, like breathing through the nose, breathing through the mouth, whispering, singing, speaking, singing softly, and singing, you can see the singing is the blue curve. It's like much, much higher emissions, and still singing softly is pretty high. And if you zoom on the bottom, it's a log scale. You can see all the other activities continue to be, less emission, but nevertheless are there. And then you basically can use that information to parameterize the model. So that's actually the primary analysis. I also tried to find other cases, and the Diamond Princess cruise ship is an interesting one to look at. There is debate over sort of how transmission happened there, how well mixed it was. But if we just take the approximation of a well-mixed ship, which is obviously a very bold approximation, and we also further assume that it's actually fast incubation. So the incubation time for the disease is around 5.5 days, and some were already infected before this period of quarantine started. So maybe it's a reasonable approximation to solve the opposite limit of the model, where every person that gets infected is able to infect others. So that's so-called fast incubation. That's also, you can solve analytically, the answer is shown here, and that's the red curve. And it fits reasonably well with the measured growth rate of cases on the Diamond Princess until they started to release people, which is when the blue curve kind of curves down. And you can get, I'll show you in a minute, a very consistent estimate, again, of that disease parameter. I also want to point out that super spreading events, all the ones I mentioned, typically involve elderly people that were obviously at higher risk because they were spreading and even dying at much higher rates than to other kinds of outbreaks. In particular, Skagit Valley Chorale, the median age was 69. On the Ningbo bus incident, the bus rider was also in her 60s, as were many of the passengers. So it's important to recognize that when we're trying to just derive a guideline, we're trying to be very conservative. So when I show you some examples of what we predict, keep in mind that we're really parameterizing it for sort of the worst case situation by looking at these cases. It's also assuming that it's only airborne transmission, so we may be overestimating the importance of airborne because we might be leaving out, say, fomite transmission. So if you do that analysis, then we can also bring in another study of respiratory droplets I mentioned by Bill Ristenpart. So that didn't look at infection, but it did measure the respiratory droplet emission rate for different types of activities, including the volume of speech. So very showing roughly that the amount of aerosols emitted is proportional to the decibel level or volume of speech, actually. So if I take Moroska's data that I showed, which are the blue bars here, and I infer CQ by parameterizing the value I get for the Skagit Valley Chorale that was actually published already by Miller's group. So that's turns out to be 970 quanta per meter cubed of exhaled air. And then I look at the droplet distribution aerosol quantities that exist in that room, as I showed, in this figure on the left here. So this is the important part, is to actually see if you were performing these other activities in the Skagit Valley Choir room, what would you see? And that allows me to rescale CQ for these other activities shown in blue. Now for the orange, which is Ristenpart's, I just do a calibration saying, well, the two activities that were kind of the closest in the two studies was intermediate speech and voiced counting, going 1, 2, 3, which was in Moroska's study. So if we just say for Ristenpart's data that we calibrate and say that those are both the same, which turns out to be 72, then now I have predictions from Ristenpart's data as well of what CQ would be. And you can see here that there's a reasonable consistency here, going from nose breathing and relaxed breathing, having CQ around 1 infection quantum per meter cubed, and that would translate to about half of emission rate of quanta per hour, all the way up to sort of in the tens or hundreds is sort of normal speech, and then singing and loud speech are actually far off to the right here. Now, I analyzed also that Ningbo bus case, so that led to an estimate of 90 here. So that seems to be somewhere in the range of speech, which might be reasonable. Also, the Diamond Princess I mentioned gives you a number of 30, which is sort of in the ballpark of quiet speech or mostly just breathing at rest, which also makes a lot of sense for people that are quarantined on a cruise ship for 12 days. And one more analysis I did was to look at the initial Wuhan outbreak. If we look at the average of all the early publications of the reproductive number, which essentially is how quickly the disease is spreading, and I make the following hypothesis that all spreading occurred indoors and at home, and I take the average size of an apartment in Wuhan, and I take the average family size, and I basically run the numbers for people sharing that space for a time which is of order the incubation time, because if you had symptoms, you would be removed. Then it turns out you get a number 30, which is again sort of roughly where we'd expect it to be for sort of light activities at home. So those are more speculative analyses, but I just want to point out there's some consistency here. So I think we can say that the sort of infectiousness of the disease and how it depends on vocalization, I think is pretty nicely captured by this plot within, say, a factor of, certainly a factor of 5, maybe even a factor of 2. So although there's also the dependence on age group and other things, also new viral strains. We've heard about the strain coming from England, the B117, which is more infectious by maybe, it's been estimated 50% or so. So one can adjust these numbers, but I think with this, we can start to be more quantitative. I mentioned here in the footnote, another interesting aspect of this analysis is that since I know the volume fractions of liquid, if I assume that that patient in the Skagit Valley Chorale was near peak infectiousness at a viral load of sort of at the peak of infection, which seems reasonable since it's probably the worst spreading event on record, and I work backwards, I find that the infectivity is around 10%, or another way of saying that is the infectious dose is about 10 virions. And interestingly, that's about 10 times worse than the original SARS coronavirus from 2003, which makes sense because that virus did not cause a pandemic and SARS-CoV-2 did. So I think that's another consistency check here, is that all this analysis leads to kind of an infectious dose that may make sense and is perhaps the first estimate of that quantity, which I'm sure will continue to be debated, but I just wanted to point that out. Now, how do you get to a safety guideline? So there are equations to solve for the dynamics of an epidemic at the population level, and you can also apply those to a well-mixed room. And I was showing some solutions on my previous slide. And those basically keep track of the number of susceptible, exposed, or infected persons in the room. But an interesting observation is that if you're only interested in cases of rare transmissions, you'd like to, engineer the room to be safe so that the indoor reproductive number is much less than 1. So notice if somebody comes in that room, we don't want transmission to happen. That's what we're going to call a safe situation. If everybody followed that guideline, we would not have any spreading. The disease would be defeated. So if we look at that, then it's interesting to point out that at early times, all these models basically tell you the same thing, which is the transmission rate, which I call the mean transmission rate, which is what I call the indoor reproductive number, is the number of susceptibles. And if you assume everybody's susceptible conservatively, you ignore vaccines, you ignore herd immunity, in a room of n people, there could be n minus 1 susceptibles. And then you multiply by essentially that transmission rate I derived. And when you go through those approximations, you can end up at this formula here, which limits what I call the cumulative exposure time. It's the number of susceptible people, roughly the occupancy, times the time they spend in the room together before the infectious person leaves. And the bound you get is a function of your risk tolerance epsilon, all the different deactivation and removal processes, such as filtration, ventilation, that I described that are lumped into lambda C. There's the volume of the room, and the denominator, there's the breathing rate squared, the mask transmission factor squared, evaluated at an effective droplet size, and then this disease parameter CQ. So let's kind of unpack that a little bit. So if n times t is less than a constant, then that curve is a hyperbola. So it's basically n goes like 1 over t. So for example, this blue curve right here. And so that's telling you that if you increase your time in a space, no matter what the occupancy is, you could be at full capacity or at greatly reduced capacity. If you wait long enough, you do cross that blue line. And that's simply because people are constantly exchanging air. And as long as you haven't hit the recovery time or removal time for that infected person, you're going to cross this blue line. Okay, so even if you're social distancing at 6 feet, you will become unsafe at a certain time. And what may be somewhat alarming when you run the numbers as I have here is that time is not really that long, actually. So while someone can infect you with a single breath if they just breathe in your face, if you share the same room with them more than 6 feet apart, let's say for an hour or several hours, you have the same or greater risk, actually. And that's very consistent with all the data that I have showed you. Now, if we want to move that bounds, if I want to take this blue curve and move it up and to the right so I can get longer times or larger occupancy in a space, it's pretty clear from the formula what I have to do. I have to increase the volume of the room so it dilutes the infectious aerosols. I can increase the ventilation rate. I can increase filtration and also see if I can do enhance viral deactivation by various methods. Now, there's also the opposite that we can, this thing gets, we can, sorry, this, yeah, this is a funny way I've written it here, but we would increase the bound or decrease if we decrease the mass penetration, or have better masks, actually. We can also decrease our breathing rate. So we know that there have been more outbreaks actually circumstantially in exercise places where people are breathing at a higher rate. Indoor sports is a cause of concern, so that's mentioned here. And also air infectious, which has this transition from singing all the way down to sort of breathing nose. Now, one nice thing the formula tells you, which I think is really missing in today's guidance, is the relative impact of all of these things. So there's a growing awareness that everything I've listed here could be important. And the public health guidance essentially is like, increase your ventilation. That's a qualitative statement. Maybe you already have great ventilation. For example, there are laboratories at MIT and elsewhere that deal with very toxic substances and even biological pathogens. How do they do it? Very high air ventilation rates. As many of you know in your own laboratories, the ventilation rate might be air change every minute or every 2 minutes. And in fact, in Wuhan was a virological lab. I'm sure that they handled viruses relatively safely for a long time using high ventilation rates. So that's obviously very important. But how high? Well, it depends on this formula. Masks are also potentially very important because that factor comes in squared. So of course, compliance with mask use is important and the type of mask, but that's generally a very significant effect. Now, by contrast, filtration is actually not as important as you think because it comes additively in the top here. And the reason for that is that you always have to have some outdoor air coming in. We need oxygen to live, and we have to have our carbon dioxide removed. So no matter how you design a space, either by leakage or by forced ventilation, there has to be a flow of fresh air through there, which means that no matter what filtration you're doing away from the source, let's say in the vents or in a freestanding unit, you can't be filtering all the air. And so even if you have 100% filtration efficiency, PF is 1, then still you essentially have the ratio of lambda F to lambda A comes in, And that's essentially controlled by the outdoor air fraction. So if you need, for example, 20% outdoor air for people to be alive or comfortable in a space, then you really can only get about a factor of 5, even with perfect filtration, HEPA filtration, or any of the other methods out there. So I think that's another very important message. So if you're thinking about, for example, investing in a new filtration system, this analysis can tell you, like, is that actually worth doing compared to maybe just finding a way to increase the ventilation rate, or as they say in Germany, simply opening the windows and maybe turning on a fan would be more effective. And then humidity plays a role, by the way, too, but it's a much more subtle and weaker effect in these. So in fact, it's my opinion that the increased case rates in the winter for influenza and also for COVID-19 are more due to the sharing of indoor spaces and indoor air rather than the humidity effect, which does also make the virus more deactivate less quickly, but it's a more, I would say, more of a secondary effect. Okay, so that's a simple formula. And so, my goal here is not just to publish an academic paper, but to try to get people and ultimately public health guidance to actually kind of use this kind of information or to debate it and modify it as needed, but to really start with this kind of pictures. So I released a spreadsheet, and also together with Qasim Khan, who was the developer, made an online app actually, which basically just applied that formula, the simple formula, but you can kind of play around with it. The app has been translated now into many languages and actually has had over 500,000 users already just since November, actually. So there's a lot of interest, thankfully, but still it's slow for these ideas to actually have the real impact I'd like to see, but at least you can play with this yourself. Now here's some examples of what that formula would predict. And, of course, any such prediction depends on the details. But if we take sort of 2 representative cases I'd just like to share with you, one is a classroom. So if you take the average classroom size in the United States, which is about 900 square feet, and you take the, estimate or sort of the difference between good mechanical ventilation and just simply natural ventilation with windows closed, where there's still a small air exchange rate, usually on the order of, let's say, 3 hours. Then you can see here how the occupancy versus time bound changes. So in the case of the natural ventilation, it's the blue, and the other one is the red. And by the way, the dotted lines are a transient bound, which takes into account the time for the aerosol to build up in the room. And so that's gives you a little bit, that's the dotted line. So basically, if you're up and to the right here, it's unsafe, as I said before. If you're below these curves, sorry, it's unsafe to the upper right. It's to the lower left. It's safe. So what you see here again is if you enforce the 6-foot rule, as has been done in all the public school classrooms in Massachusetts and in many other places, what it ends up doing, it roughly cuts the occupancy in half. By the MIT did the same thing. But really, how much are you buying there? You're maybe increasing your safe time in the room by a factor of 2. So is that really worth the disruption of shutting down all the schools? And I'll come back to this issue in a moment. But even at MIT, actually, versus just having normal occupancy, and instead, for example, paying closer attention to ventilation and filtration, and also just looking at the time in the room. And one interesting observation here from my analysis of different classrooms is that children are generally safe with masks, and even without masks are still not that unsafe, especially if there's testing or checking of students on the order of days. Now, there's some interesting data that's starting to back that up from the National COVID-19 School Dashboard, maintained by Emily Oster, where they have the data for all the different schools, some of which are in person, some are not, some are wearing masks, some are not. And interesting observation is that if you look at the trends as you go to increasing time in the classroom versus hybrid model where students are on Zoom, that the case rate for children actually goes down. And that's consistent with even my own experience. We just had in my town, our high school had 10 cases last week. We were already in hybrid mode doing half on Zoom. And so they shut down the high school. And my daughter's friends are all basically hanging out with each other without masks and wandering around town, or in some cases leaving the state. So there's an argument to be made that actually in school, with all the restrictions that are placed, and in particular at the university where there's even more maturity and ability to follow restrictions, we can actually be very safe. So it's a message I want to get across. On top of that, though, I'm not saying we shouldn't worry about COVID-19. Clearly, as I showed you, it's a terrible disease for the elderly and also some other groups. And so we have to protect those people. One way is by trying to limit transmission. That's what the current strategy is among everybody, even the healthy asymptomatic people. But also we could just look a little bit more closely at the spaces those people are in and really focus on how to keep them safe. And this is where I've now, by the way, lowered the tolerance for transmission to 1%. So it's this is one reason the numbers are going down. And also, if you take a typical nursing home room size in New York City, and by the way, regulations limit occupancy of 3 in one room, then the 6-foot rule would tell you 2 in one room. And they were literally doing that. You put the beds 6 feet apart, and therefore you must be safe. But actually what it shows you here is that the transmission time is very low. We're talking in the order of much less than an hour. In fact, close to the CDC definition of 15 minutes as a transmission time. And so we should be very careful about people coming in from the outside who are in contact with these people, and really also work on increasing their ventilation, just being more aware of the hazard of airborne transmission. So I think that's still also a very important case. And there are other situations also to watch out for, but that's just 2 case studies. Now, let me briefly conclude by describing how we might go beyond the well-mixed room and see, what are the kind of limitations of the analysis I just showed you. And so first of all, there's definitely variation in a room. And in some cases, you even try to do that. So you've probably noticed in restaurants and in some workplaces, erecting partitions to try to sort of contain air around a smaller number of people in order to limit spreading. Although an interesting observation is that actually, if the population density is uniform and you cut the room in half, you have no effect actually, because you have a higher concentration for those people. And also many of the partitions that are put up, when you think about airborne infection, the air just goes right around those partitions. And so there's very limited benefit, but nevertheless, that's one topic of considerable interest right now. These videos here from the work of Linden's group at Cambridge, I think are very beautiful. He has been focusing on ventilation effects, but also visualizing through Schlieren methods, the flows when people are breathing. And here you see the fact that just the warm air around a person's body tends to rise. So we're kind of all like chimneys, and there you see a breath. And so it shoots out a bit, and definitely your breathing when not masked has a lot of momentum. So even if you're not sneezing or coughing, you're pushing the air out. And so it does travel further and starts to close to your neighbors, but notice that's warm air, and it actually also rises. So we're kind of a bit more like chimneys than projectiles. If you think of, at the supermarket, these small plexiglass windows, it almost looks like on the side of an armored vehicle, to block bullets, as if someone's going to be spitting, on the cashier. But actually, this is a better picture of what's actually happening. Here's what happens with masks, and you see the importance of fit and compliance. Oh yeah. Oh, see, he's talking, right? Sorry, I was like, who's talking?
With COVID-19
yeah.
went viral during lockdown.
Yeah, right. Anyway, so he's talking, and so you can see the momentum of the air is completely blocked. So this kind of respiratory jet that would happen is completely blocked by a mask, even a bad mask. But then also the filtration effect is there, but anything that leaks out does tend to rise. And so that kind of helps us with some of the short range effects that could be important when you're not wearing masks. So that's number one. And also that ventilation studies need to consider also thermal effects as well. So I think I want to leave you with kind of just a nice way to think about airborne transmission, which is there really are 2 types. Is that if people are not wearing masks, then it's really like being in a smoke-filled room with smokers. And I think many of you have been in that situation. It's less common today than it used to be, but certainly I think we're familiar. When a person exhales smoke, if you're standing directly in that plume, obviously you're taking in a very large amount of smoke if you breathe in at the same time. And so those turbulent plumes kind of need to be avoided. But we're very aware of that. So people that are smoking tend to blow in a different direction. It would not be good manners to blow directly in somebody's face. But we also know that if you spend time in a room full of smoke, there's always a localized sort of area of smoke around the smoker. But then very quickly, the entire room is full of smoke. And it happens on the scale of the air change time or the mixing time in the room, which can be on the order of 1 hour or even tens of minutes, or in some cases even less. So we have to worry about this airborne transmission. So here's actually from the CDC's own website, they do understand airborne transmission when it comes to smoke. In fact, they even tell you smoke can penetrate to apartments that you're not even in through hallways and stairwells. And there's some very recent studies that have now shown that for COVID-19. A Korean apartment building just recently was shown to have infection patterns that followed the vents in the building among people that never came into contact. And so the sketch on the right is exactly right. There's kind of this demon in the air, but it's not smoke, it's actually infectious aerosols. And I think the sooner we recognize that, the better, because right now what we're doing is washing surfaces all the time and standing 6 feet apart. And distance is good. I would rather have people distance than not distance, but we need to really acknowledge this airborne transmission in order to, I think, devise more effective means of safety and also even contact tracing. I'll just briefly finish here just with a little more analysis for fluid mechanics for this engineering audience. So from the work of originally John Bush on the sneezing and even going back to Wells, and more recently Howard Stone's work with Abkarian on just normal speaking. Basically respiration, as I showed you in those movies, essentially creates turbulent puffs, and just breathing normally, those puffs kind of catch up with each other and make a puff train that looks a lot like a continuous turbulent jet. And so by using the beautiful theory of turbulent jets, you can see how the concentration of infectious aerosol decays with distance in the jet. And you can even go back to the guideline I showed you and basically calculate a correction based on what is the probability that someone is actually exposed to that jet or plume. And that's where social distances can come in. So X here is the distance at which you're typically sampling that plume. So if you want to look at a situation like a restaurant or a meeting where people are not wearing masks, this term can be very important, actually. In fact, can be larger than the other terms. So I would say when people are wearing masks, the guideline I derived, I think, is actually very, very reasonable and in fact, very accurate. When we're not wearing masks, there can be elevated risk from short-range transmission, and that can be larger, although the effect won't be enormous unless you're like right in somebody's face, but it can be a factor of 10 or more, and that should definitely be taken into account when deciding, when to finally remove masks and go completely back to normal. So that's just important to be aware of that. So I'll just conclude with here a link to my website, which basically helps you find the online app if you're interested in playing with that. I also have a massive open online class on edX, which just launched last month. It's free, it's self-paced, and it kind of goes through the science of transmission that I presented today, plus even some additional details called Physics of COVID-19 Transmission. So thank you for attention. I look forward to your questions.
Great, thank you, Martin. Let's thank our speaker.